Alright, so you spent the last lesson looking at simple interest, and I mentioned that that wasn't the most realistic way of doing interest because that's not how most interest is calculated. Most things out there, bank accounts, credit card loans, things along those lines, are calculated using compound interest. And the difference is, with simple interest, the interest is only calculated based on the original investment or your original loan. Um, in real life, with compound interest, interests are not just on what you originally borrowed or invested, but on all the accumulated interest as well. So if you think about what that means, if you look at an example here, we saw something like this last lesson. We had an investment of $4,000 earning 3% a year. When it was simple interest, well, we'd find 3% of what we did in the first year. So 3% of 4,000 is 120. So our investment's worth 4,120. With simple interest, though, we would have gone up by $120 every single year because, again, the interest is only calculated on the original principal of 4,000. Now, if we want to find our total value after 2 years, we're not taking 3% of the original $4,000. We're taking 3% of our new investment value, which is 4,120. So if you do 3% times 4,120, run that through your calculator. Okay, you get $123.60. So when you add that to 4,120, you get $4,243.60. To find the following year, now you're taking 3% of that amount, $42.43.60. So you calculate that, you add it to the original, and you get 43.70, and so on and so forth. 3% of that added to 43.70 gives you 45.02, and so on and so forth. So you'll notice here, looking at the table of values here, that your differences are no longer constant. Okay, with simple interest, we had constant first differences. They're all 120 when we're looking at this example, if you want to go back and check. Here now, we're going up by different amounts every single time. Okay, so if you take a second and calculate those differences, you're going to get 123.60. Okay, and I'll just take a minute here and go through the rest. You should too. Okay, you see the rest of the differences there, and again, you'll see they're not constant. So we've got to figure out what kind of relationship this is. You could take your second differences as well, and you'll find that, again, they're not constant either. What's actually happening here, we checked our first differences, we can check our second differences, you can do that on your own, you'll see they're not the same. What we can look for is a common ratio. Okay, so if I divide 135.06 by 131.13, I get approximately 1.03. If I do the same thing here, 131.13 divided by 127.31, again, 1.03, and ditto here. So think back over the course of the year. What kind of functions did we look at that had relationships where the differences had constant ratios? Well, those were exponential functions. So the relationship between, with compound interest here, is going to be exponential, not linear like simple interest was, but again, exponential. Okay, so that's the relationship we have here. So that means the equation that we have to deal with compound interest should look somewhat exponential, should have that kind of general form. Okay, so a couple definitions to bring yourself up to speed on first. When you see the word compounded annually here, when it says compounded annually, that means the interest is calculated and handed out or charged every year. There are situations where the interest will be compounded monthly, so every month the interest is either added to your account or charged on your account if it's a loan. You can have things compounded weekly, daily, quarterly, and it'll change things slightly as we go, but keep that in mind. That's what it means if something is compounded at a certain time period. Okay, so our equation for compound interest looks something like this. So it's a equals p times bracket 1 plus I to the n. Now, think about what this means here. I'll talk about what all the different variables mean, but this really is just an extension of an exponential function, y equals c times a to the x. If you picture that since it's interest, our investment or our loan amount is going to be increasing, well, this is really just, if you remember that a was equal to 1 plus a growth rate, this is really the exact same thing, just with different variables, right? My y is my a, my initial value, c was now p. My variable has, my growth rate changed from r to I, dealing with the interest, and sorry, this was an x. My x is now my n. So it's really just an extension of that, just the different variables in its place. So you can see this is really going to be an exponential function. But let's talk about what these different variables mean. Okay, so in this, what we have is, first off, A is going to be my final amount. Okay, so you should have this down in your notes, all the different parts of the compound interest formula. So it's final amount or final value of the investment or loan amount. Okay, P, just like with compound interest, or sorry, just like with simple interest, is going to be your principal. So again, that's your initial investment or loan. Okay, now I is going to be your interest rate. But the difference here is it's going to be interest rate per compounding period. And that's a thing that can confuse a lot of people, because you're going to get an annual interest rate. But if the interest is compounded, let's say, every month instead of every single year, if your annual interest rate was, let's say, 10%, they're not going to give you 10%, or they're not going to give you 10% or charge you 10% interest every single month if it's compounded monthly. They're going to spread that 10% over the 12 compounding periods that you're going to have per year. So I'll talk about how to calculate that, but really what happens is you take your annual interest rate, and you divide it by number of compounding periods per year. So in terms of number of compounding periods per year, that again depends on how often it's compounded. So if the interest is calculated or compounded every month, then you're going to divide it by 12. If it's compounded per day, you're going to divide it by 365. Okay, and last but not least, you have n, and n is the number of times the interest is compounded. So number of compounding periods. Okay, so again, to calculate that, let's say your interest is compounded monthly for 5 years. Well, monthly would be 12 times in a year. 5 years, 12 times 5 would be 60 times the interest is compounded or calculated over that given investment time. So here you would take your, in general, you take your number of years and multiply it by the number of periods per year. But we'll see all this when we do some examples coming up. Okay, so if you have all these variables right here, you can put them into the equation, solve for basically whatever you need to. Okay, so it might seem confusing right now. Let's take a look at some examples here. So again, the tricky part with dealing with this compound interest formula is usually dealing with I and n, because those compounding periods come into play. A and P are pretty straightforward. It's the final amount of your investment and the initial amount you invest. I and n can be a little bit tricky. So I'm going to give you some different situations here, and you're going to try and tell me what I and n are. So let's start off with 17 years at 6% per year compounded quarterly. Okay, I'm going to do my calculation underneath here. So for my interest rate, okay, remember, it's the interest rate per compounding period. So I've been given it's 6% per year. So first thing I'm going to do is convert that to a decimal. Okay, so I convert 6% to 0.06. Now it's compounded quarterly. Quarterly means every 3 months, or what might make more sense is to think it as 4 times per year. So that means 4 times over the course of the year. If it's an investment, they're going to calculate the interest and give it to you. If it's a loan, they're going to calculate the interest and charge it to you. So 4 times a year means you take 0.06, divide it by 4, and that's going to be the value of I that goes into your equation. So 0.06 divided by 4 should give you 0.015. Okay, now for n, it's 17 years, compounded quarterly, compounded 4 times a year. So that means over the course of your investment, it's compounded 4 times a year for 17 years. 17 times 4 is 68. So you'd be putting 68 into that equation for n. Okay, so again, once you get used to it, it's actually not too bad. So you take your annual interest rate, divide it by the number of periods per year to get I. You take your number of years and multiply by the number of compounding periods per year to get n. Okay, let's do one more together, let you try the rest on your own. So 5 years at 10% per year compounded semi-annually. So semi-annually means twice per year. So 10% is 0.10. Twice per year divided by 2, that means your I is going to be 0.05. Okay, for n, it's 5 years at twice a year, so the n is going to be 10. Okay, that's obviously a typo in your equation, in your lesson there. That should be 10. 5 years at twice a year. Okay, so there's 3 more examples that I'd like you to try. Try them on your own first, either on your own or with a group. When you get an answer, push play and you're ready, and we'll go through them together. Okay, so you can check your answers here. For the third one, 3 years. Let me start with I. So I is 8% a year, which is 0.08. Monthly is 12 times a year, so 0.08 divided by 12. Now you notice I didn't put this in decimal form here because it's not an exact decimal. I would just to keep accuracy, I don't want you to round if you because your answer is going to be very, very inaccurate. So keep it as a fraction if you need to, and put that in the equation. So for this, just leave it as 0.08 over 12, and you put it into the formula if you have to use it. So for n, you have 3 years and 5 months, which is 41 months, which is 41 over 12 years. So 41 over 12 years times 12 times a year, those 12s cancel, and you get 41 as your n value. Okay, for the fourth one, 15 months, if you're looking at n, 15 months is 15 over 12 years. Weekly is 52 times a year, so 15 over 12 times 52 is 65. For I, 3.25% is 0.0325 divided by 52 to give me that. And last but not least, compounded annually. Like the very, very first example we did in slide 1, this just means once a year. So really nothing needs to be done. The 4.5%, you turn to a decimal, divided by 1, stays the same, 0.045. The 6 years and 5 months, when you convert that to years, 6 years is 72 months, plus another 5 months is 77 months, so you get 77 over 12 years. And since it's compounded annually, it stays the same for n. Okay, and again, once you get used to figuring out what I and n go into the equation, it becomes a lot easier. Your answers won't make a lot of sense otherwise, so you have to make sure you're making those conversions. That's really a common mistake that people tend to make. Okay, so let's do some examples here. So now we're borrowing $4,500 at 3% a year compounded quarterly. We want to figure out how much we owe after 5 years and 4 months. Okay, so first thing you want to do, once you see the word compounded, you know you're dealing with compound interest. You can start writing out your equation. So A equals P times 1 plus I to the n. And just a matter of figuring out what goes where inside the formula. Okay, so we originally borrowed $4,500. That's my principal. I want to know how much I owe in total, so that's going to be my A. Okay, I've told it's 3% per year, so I'm going to convert that to a decimal. It's compounded quarterly. Quarterly is 4 times a year, so it goes 0.03 divided by 4. Okay, which I can simplify down into 0.0075. Okay, and last but not least for my n, so I have to convert everything to years first. I have 5 years and 4 months, so we need to be able to do some conversions here. So 5 years is 60 months, so 60 months and 4 months will be 64 months, so my number of years is 64 over 12. Okay, but it's compounded quarterly again, so I have to remember to multiply that by 4, so that's going to simplify into 64 over 3 compounding periods. So that's what goes into the equation for n. Okay, once I have that, it's not actually too bad. I just need to sub everything into my equation. So I have A equals, my principal is 4,500. I have 1 plus 0.0075, all to the exponent of 64 over 3. So try running that through your calculator, see if you can solve for the final amount, and push play ready to see if you've got it. So I get a final amount of $5,277.65. Again, 2 decimal places is a good final answer to round to when you're dealing with money, because it goes down to the cents. So if you can't get this to work out in your calculator, let me know, because there's usually a bracket issue that we can work out. But that, in general, is how compound interest works. Okay, so let's take a look at the next example here. I want you to think about it, and we'll look at it in part 2.